Here's the rest of section 5. Talked about work and kinetic energy last time. Leading up to the idea of potential energy, we start with the idea of a conservative force. The definition is what it says there. The formal way of defining it is a conservative force is one where the work done is independent of the path taken. So let's say you're going to move an object from point A to point B over here. This could be a box you're dragging across the floor, or it could be something that sits on a shelf here, and you pick it up and you lift it and put it on a different shelf up here where it's higher. Well, if you're lifting it from one shelf to another, the amount of work you end up doing is going to be the same, whether you go right straight across like that, or whether you follow this rather circuitous path that I've drawn here, because gravity is an example of a conservative force, okay? When the box goes down, gravity is doing, well, whether it's positive or negative, I guess depends on whether you're talking about the work done by gravity or the work done by your hand as you lift it. But if you talk about the work done by the pull of gravity, that would be positive as you go down and negative as you go up. And when you add it all up, it's the same if you do all of that as it is if you just go right straight across like that. Friction, on the other hand, is an example of a force which is not conservative. You will find that it's more work to follow the longer path than it is to follow the shorter one. So anyhow, that's the basic definition. That's what the word conservative for, or the phrase conservative force means. Now, let's apply that to the special case where A and B are the same point, drawn down here in the corner. If A and B are the same point, one way of getting an object from A to B is to not touch it, because it's already there. So getting from A to B takes zero work that way. And if it's a conservative force, any other way of getting, moving it that ends up back at its starting point is also going to be zero work, which means, for example, in the case of gravity, as you lift an object up, you are doing work on that object. As the object comes back down, work is being done by the object. It can do work for you as it falls. So positive work on the way up and negative work on the way down. If you're talking about the work done, by your hand as you lift it. And so in the end, it's a total of zero, but notice that this type of force can be used to store up work, okay? You do some work lifting the thing up, and then, like if you had a little box sitting on the shelf here, then, an elevated object. So I shouldn't be showing you all these invisible things. Just a second. Okay, well, the string that I've got a stapler over here, and I've got this box here, and the string that connects them is still something I'm sort of imagining. But the idea is, because the stapler is elevated, if I let go of it, it'll drag this thing along. It'll exert a force through a distance. So an elevated object is capable of doing work. Okay? I have to do work on it as I lift it up, and then it can do work for me on the way down. And so conservative forces can be used to store energy, contrasting with, for example, friction, where I have to do work against friction on the way over, and I still have to do work against friction on the way back. Friction converts energy into a non-mechanical form instead of storing it up for me. So that's, see, all the energy you put in one direction comes back going the other way, so the energy is conserved. That's where we turn the page. But before we get to what it says on the next page, well, no, actually, what says on the next page is the next thing. And then we'll look at some other stuff. The work done by any conservative force can be represented by a type of potential energy. And there are several different types of potential energy. The work done by anything that stretches, a spring or a rubber band or something like that, that work can be thought of as a change in elastic potential energy, which is a topic we'll look at later in this course. Near the beginning of Physics 132, we'll look at electric, or I called it electrostatic potential energy. Well, that's a story for another day also, but that's the work that an electrically charged object could do in an electric field. But for what we're going to talk about right now, a mass can do work because of its position in a gravitational field, as I've already talked about with my stapler and all of that. Just how much work is it capable of doing? I will escort you to the other end of the table here and write some stuff down. Gravitational potential energy. First of all, what it means in words. Words, gravitational potential energy is the work an object could do dropping a distance h, h for height. This thing is some height h, perhaps above the floor. Well, work, we'll just look at the simplest case. I mean, if you're going to be really general about things, you'd have to consider the case where an object maybe moves at some sort of an angle. Well, let's be a little less rigorous and a little less time consuming. And just consider the case where something goes straight down, in which case work that an object could do in dropping a distance h would be the force that it can exert times the distance that it can exert it through. Well, this object is capable of exerting a force equal to its weight. An elevated stapler or whatever it is, if there's a string tied to the stapler, it can create a force in that string equal to the weight of the stapler. And as the stapler falls, it can exert that force. Why is there a little menu right in the middle? Well, okay. Just wanted to make sure I wasn't muted or anything like that. An elevated object can exert a force equal to its weight through a distance equal to its height. So the moral of the story is the symbol we're going to use for potential energy is a capital U. That, I'm pretty sure, is the notation that's used in the textbook. Although if you want to abbreviate it PE, you can't imagine how little I care. But this is the way I'm going to do it anyhow. And the subscript, because there are different kinds of potential energy, elastic potential energy and so on. UG for gravitational potential energy. Mass times the gravitational acceleration times the height. Which then brings us to number 6. So you've got some sort of an object hanging off of a rope in the middle of a room. Well, I shouldn't say the middle, it's slightly below center. It was kind of popular for a while to hang spider plants. I haven't seen that so much lately, but this could be some flower pot with some thing growing in it. And this might be a system of ropes rather than a single rope, but it's easier to draw this way. Anyhow, whether it's a spider plant or something else, whatever it is, what is its potential energy if it's a 3-kilogram object? Well, you will never see a question phrased exactly like this one on a test I give you, because the way that's phrased, anything could be the answer. You know, if you are fond of the number 42, you could write down 42 joules and put a little box around it and go on to the next question, because like it says in parentheses, potential energy is mgh. Okay, height relative to what? You can measure the height from any level that you find convenient. Once you start a problem, you have to stick with the choice you've made, but just as a couple of possible answers to this badly worded question. Potential energy relative to the floor kilograms, G is 9.8, and based on the dimensions given in the picture, the object is 1.5 meters above the floor. So relative to the floor, the potential energy is a little over 44 joules. But why relative to the floor? You could just as correctly measure the potential energy from the ceiling. GH again, 3 kilograms times 9.8. Relative to the ceiling, the height is -2 meters because the plant is below the ceiling rather than above it. Positive potential, and remember, work and energy are scalars. So plus and minus signs are not directions. Rather, a positive potential energy means that you can get energy from this mass as it returns to the level you have defined to be 0. A negative potential energy means you have to put energy, you have to give energy to it in order to get it up to where you said its energy would be 0. Okay, that's what's going on with the plus and minus signs. Anything measurable depends only on the change in potential energy. So potential energy itself is arbitrary. Measure the height from anywhere you want. If you're trying to calculate how fast this plant would, if somebody came along with a pair of scissors and cut the rope, how fast would the plant be going when it hits the floor? The speed of the plant, that's something measurable, and it depends only on how much the potential energy changed, okay? Whether it goes from 44 down to 0, just a moment, I'm going to pause right there. So to kind of summarize what has happened so far in this unit. The word energy, once again, means the ability to do work. An object that's capable of doing work possesses energy. There are several different ways that an object can be capable of doing work. In other words, several different ways that energy can be stored in an object. Kinetic energy is the energy that or is the work that an object could do because of its motion. The example I usually give there is a hammer. As it approaches a nail, it has kinetic energy. As the hammer strikes the nail, there's going to be a force. The hammer pushes on the nail, and it acts through some distance as the nail gets pushed into the board. So if something can exert a force through a distance, that means it's capable of doing work. And what makes the hammer capable of doing work is the fact that it's moving. Potential energy, the work that an object could do because of its position. How high is a mass located in a gravitational field? Or where is a charged object located in an electric field? Or if an object is attached to a spring, how far has it been moved from where the spring would be its equilibrium length, that sort of thing. Kinetic and potential energy are the forms that we're going to be talking about for the time being, because at the moment we're looking at mechanics. Physics is a subject with several different branches, and the branch we're in right now is called mechanics. But there are also a number of non-mechanical forms. Chemical energy, I put on there as an example. If you put some gasoline in the cylinder of an engine, the gasoline is capable of going through a chemical reaction that will cause a lot of pressure to build up in the cylinder. That'll push the piston down the cylinder, so you've got a force acting through a distance. It's doing work. And the thing that makes the gasoline capable of doing work is this chemical reaction. Or another example of chemical energy is if you throw a ball. Where did the kinetic energy of the ball come from? Well, it was, before you threw the ball, it was in chemicals stored in the muscles in your arm. Heat is a kind of energy. You can build a fire under a steam engine and it will exert a force through a distance. And there's other examples also, but let's move down to where it says more on the work energy theorem. There. So there's what I had earlier in the previous recording. The work done on an object equals the change in its kinetic energy. And there, one more interruption. Just for future reference, if you wait for me to not be in this room, I'm not sure if that's ever going to happen. So just knock, and hopefully I'll actually succeed in pausing the video next time. Sorry about that interruption too. Let's take the work and kind of divide it into two parts. I'll write this down in a second, but forces are either conservative or non-conservative. Let's take the total work done by all the forces acting on the object and say that it's equal to the work done by the conservative forces plus the work done by the non-conservative forces. So C for conservative. I'll abbreviate because I'm starting to run out of places to write. So NC for non-conservative. Well, it says, I think it was at the top of this page in that note packet, that the work done by conservative forces can be thought of as a change in potential energy. So of course, there's always some nitpicky minus sign that has to be explained. If you want to get into the details, the work done by a conservative force is not actually equal to the change in the potential energy. It's equal to the negative of it. Because, like, for example, consider a falling object. The farther it falls, the more work has been done by gravity. The farther it falls, the less potential energy it has left. So as the work gets bigger, the potential energy gets smaller, and that's why you need a minus sign in between them like that. Because if W is a positive number, delta U would be a negative number. U would be decreasing, and decreases are negative. Anyhow, substituting that into the work energy theorem, minus delta U here, and then maybe I should have written it out as two separate lines. I kind of did two things at once. I put negative delta U here, and then I added it to both sides, which makes the relationship into that. Let's have a symbol to stand for, rather than say kinetic plus potential over and over and over again. Let's have something that stands for that. Total, well, technically total mechanical energy. When people are not choosing their words carefully, this often gets called the total energy, but it's not really the total energy. It doesn't include chemical energy. It doesn't include thermal energy. There's lots of non-mechanical forms that energy can take on, but the total of kinetic plus potential is often a useful thing to talk about. So, substituting that into the line above it, the work done by non-conservative forces equals the change in this total mechanical energy. Delta E, of course, means E final minus E initial. And if you rearrange that a little bit, that becomes my personal favorite way of writing the work energy theorem. Initial energy plus, quite often, you'll see me just write a W and kind of leave the NC subscript understood. But, well, for example, if the only conservative force present is gravity, this would be the work done by forces other than gravity. If you include the work done by gravity in this term, see, the work done by gravity is the change in potential energy. If you include it here, you're counting it twice. Okay, so non-gravitational forces like friction or like somebody pushing on something, that's what goes in there for W. And I may get lazy and leave off the subscript. Initial energy plus work done equals final energy. It's just like pouring water in a bucket, okay? Because doing work amounts to adding to the energy that something has. So the amount you start with plus the amount you add equals the amount you end up with. If you've got 3 quarts of water in a bucket and you pour in 2 more quarts of water, you've got 5 quarts of water when you're done, and energy behaves the same way. Non-conservative forces just transform energy in or out of mechanical forms. So in the broader sense, energy is always conserved, okay? This mechanical energy E is only conserved in the absence of non-conservative forces. See how the terminology works? If all you have are conservative forces, then E initial equals E final, energy is conserved. In the broader sense of the word energy, when you include heat and everything, then energy is always conserved. So back to the handout. So E initial plus W equals E final. Non-conservative forces just transfer energy into or out of a mechanical form. So the total energy of an isolated system, when you really mean the total energy of an isolated system always remains constant. Conservation of energy, where the word to conserve means to keep the same, basically. Conservationists don't want the swamp to change. People who are politically conservative don't want the country to change. And conservation of energy means the amount of energy that's there doesn't change. Oh, let's see. I guess it's time to do the next example. Well, one little comment to interject. I haven't actually looked at the current edition of the textbook, but I'm pretty sure it's the same as the couple of editions previous to that. I guess I was looking at the 8th edition at the time I wrote this in my notes here. But one of the authors goes on and on about how there are difficulties, some subtle difficulties with the idea of the work done by friction, and so, you know, as the surfaces slide across each other, they are deformed as they get dragged, and he goes in this whole big elaborate thing and refuses to call the force of friction times the distance the thing moves work done by friction. And I guess he's got some good reasons for that, but my attitude is that physics books are full of approximations. Well, not all physics books, but the textbooks for introductory courses like this one, freshman level physics books, they're just full of frictionless surfaces and massless ropes and ideal gases and all sorts of things that are just approximations to reality. So why not sliding objects whose surfaces don't deform as they slide along? And the whole book is just an approximation to reality from one cover to the other. Anyhow, you get into more advanced courses and they start cleaning up some of that, but let's just say force of friction times distance with a minus sign on it is the work done by friction. And John Jewett, the author, he can just deal with it. I actually worked with him many, many years ago, but it's time to do number 7. So you've got this book, and it falls 2.5 meters, and you're supposed to figure out how fast it's going when it hits the ground. Well, you might look at that and say, oh, we could have done that the first week. V final squared equals V initial squared plus 2A delta X. And if you looked at it that way, you'd be right. That's a perfectly good way of doing the problem. And actually, in this case, it might even be the most straightforward approach, although using energy methods isn't really a lot more difficult. But anything you can do with work and energy methods, in principle, can be done with methods from earlier in the course. Because I showed how to derive all of this stuff from things that are earlier in the course, F equals ma and so forth. So therefore, anything you can do with this, you could do in principle by using those things that I derived this from directly. In practice, it's nice to have alternatives, because sometimes one alternative is nice, sometimes the other alternative is better, okay? In this case, it doesn't make that much difference which alternative you use. I'm going to do it using energy methods because that's the part of the course we're in right now. So E initial plus the work done by non-conservative forces equals E final. And because there are no non-conservative forces, the question says that there is no air friction, or at least there isn't enough to be worth thinking about. Because there are no non-conservative forces, that's 0. E initial will equal E final. Now, writing this out in twice as much detail as it's actually worth, just because it's my first time through something like this, E stands for, like it says over there at the other end of the blackboard, it's kinetic plus potential. 1/2 m the initial squared plus mg h initial. It says the book was dropped from rest, so therefore v initial equals 0. Kinetic energy means the energy of an object's motion. If it's not moving, you don't have any of that. Over on the other side, E means the same thing, kinetic plus potential. Stick a bunch of F's all over it for final. This time it's the potential energy term that's 0. Or at least it is if you've got any common sense. Now, as I said earlier, you can measure the height from any level you want to. And if you enjoy making things more difficult for yourself, you could measure the height from somewhere, 0.5 meter above the floor, which would make H initial 1 meter and H final negative 0.5. And I'm sorry, H initial would be 2 meters and H final would be negative 0.5. It starts out 2.5 meters above the floor. But why would you want to do that? It's always easier to drag fewer numbers around than it is to drag more numbers around. So the sensible thing to do is to say that H final is where you're going to measure the heights from and make this term equal to 0. let H final be where H equals 0. That wipes that out. So if this wasn't my first time through a problem like this with you, I would have only written about half as much down. I would have just said the energy starts out in the form of potential energy. As it falls, the potential energy changes into kinetic energy, and it's all kinetic in the end. And I would have just written down mgh equals 1/2 mv squared. But I figured I'd better explain where all the other stuff went. Time to slide you over a little. Question did not tell us the mass of the book. Doesn't matter. Mass drops out anyhow. As I said earlier in the course, anything, any free-falling object drops at the same rate. So mass doesn't matter. Divide through by m and it's gone. V final is the thing I'm looking for. To solve for V final, I'll multiply both sides by 2 and then take the square root. Maybe you can see here the resemblance to that other equation I mentioned, V final squared equals V initial squared. V initial is 0 plus 2a times delta x. Falls 2.5 meters. And just happens to come out even. Back to the handout. Got to go a little higher. Now, as I said before, alternatives. You could use an energy approach, or you can use an F equals MA type of approach. You know, F equals MA and other relationships from earlier in the course. This one actually might have been slightly easier using things from earlier in the course. This one, on the other hand, in principle, you could do it using relationships from earlier in the course. In practice, well, the problem is this. This child has a variable acceleration. First, the kid's gaining speed, then the kid is losing speed, and then the kid is gaining speed, and then the kid is losing speed. As the angle of the ground beneath the child continuously changes, the acceleration continuously changes. So if you're going to use methods from earlier in this course, what you would have to do is take the entire, what does the answer turn out to be? It's a little over 97 meters. So you have to take the whole 97 meters, chop it up into little pieces small enough that the acceleration is constant in each little piece. This, looking at things this way, will allow you to set up a differential equation, which, why don't I just stop there in mid-sentence? Why would you want to go through all of that when an energy approach is 3 or 4 lines of elementary algebra? Okay. Looks like this. anytime you're going to use work and energy to solve a problem, your general jumping off point is E initial plus W equals E final. Work done by non-conservative forces. And if it's a problem, like the previous one where it's just E initial equals E final, that's still this, just with W set equal to 0. In this case, though, the work is not 0 because friction is present. Just like in the previous question, the initial energy is in the form of potential energy because it says on the picture that the child starts at rest up on top of the hill. Okay. So because the initial kinetic energy is 0, the initial energy is equal to mgh. For the work, I think I might have mentioned in the recording for the first half of section 5 that work done by friction will always be minus F times S, but just to go over the reason for that again, just in case I didn't say that, if you take, like I said, the answer comes out 97 meters for the total distance that the kid goes. If you take just a small piece of that 97, small enough that it moves along pretty much a straight line, then this would be the displacement vector S. And the little box is supposed to be the child sitting on the sled. The relevant phrase is friction always opposes motion. So no matter which way the child is moving, friction always points the other way. When the kid is going downhill, friction points uphill. A little while later, when the kid's going uphill, friction points downhill. The direction of the F and S vectors vary as you go along this irregular landscape, but as, let me get something else here. Pen is the one vector, the pencil is the other vector, and as the tilt of the land changes, as the child goes along, the direction of the vectors changes relative to horizontal, but they do not change relative to each other. There is always if you stick these two arrows together, they always make 180 degrees anywhere along the whole path. Friction always opposes motion. When it's friction, the angle is always 180 degrees. So that's where that comes from. In this or any other problem involving work done by friction. And in the end, the child is no longer elevated. And has coasted to a stop. So what's going on is there was originally some potential energy because the child was elevated, as the kids slid along, that energy was converted into heat, basically, because of work done by friction. And so in the end, it's gone. It's dissipated into the environment. Adding F times S to both sides, we've got that. The question is, how far does the child slide? That's asking us for S. It's even labeled S on the picture. Fill in the numbers and we've got it. The original height is 15 meters above the level land below the hill. Average friction force is 83 newtons. That would vary a little bit as you slide along because the normal force would be changing with the changing tilt of the land. $97.4 meters. Of course, you always go a little further the second time if you manage to slide down the same spot again, because you got the snow compacted from the first time you went through. But the question doesn't ask about that. So that's the end of section 5. And let's see if I can actually manage to click on stop this time instead of letting the camera run forever like I did last time.